Welcome to yet another exciting topic on deep neural networks, and this is where we are going to continue from our previous discussions on neural networks, and that was about using a very simple neural network, and then we use just 100 neurons over there to train and then classify these microscopic images of WBCs into whether they are leukemic or they are not leukemic. Now here I'm going to speak about something which is quite upcoming in the community and actually has got the community by a buzz, and that's called as deep learning. And neural networks are in fact one of the major runners in this whole family of deep learning engines in which we are going to work. So, but before I start down, I would come down to this basic definition of learning. Now, when we say learning, it's not by definition that there should be a set of features and then I should be able to classify something and do it. This is one of the major misconceptions people have in their mind. So this can be a regression problem, as we had seen down for decision trees and random forest as well. And for a very simple stuff, let's define what this learning is. And the definition which Tom Mitchell puts down is quite simple. He says that a computer program is said to learn from experiences E with respect to certain class of task T and performance measure P. Now you would be saying that it is learning only if its performance at a task T as measured by P is going to improve with experience E. So you need to know one thing, that since we have already done that basic class on neural networks, so one thing in mind is that this experience is the number of epochs and the number of times you are looking at the same data. Now as you were looking at the same data, as the whole neural network was looking at the same data, it was trying to look at the data and find out what is the error and then again back propagate this error. This was the looking back phenomena on it. Now as it was updating itself, what you could see is that it was doing the same task, which was just classifying the data, but the measure of performance, which is P, which is that cost function over there, was increasing as it was looking at more number of samples over a longer duration of time, the same samples over multiple number of times or a larger number of samples. So that's where we said that the neural network was learning, because this definition was being satisfied over there. Now over here, as per the definition and by its own basic concept, it's nowhere said that you need to have features over there. Nowhere we are saying that you need to be able to classify. Now that's where we get into the actual problem. Now if we look into learning as its own paradigm, I would take a very simple example from very scenic images, and I'm not going to take down very specific medical images over there, because you need to have a much wider understanding for them. Let's look at a very simple problem of scene image classification, and on that, let's say that this is one of the images which I'm going to take. Now you would often be seeing just if you haven't been to this particular place, then what you would be seeing is just 4 people over there. Somehow if you are looking into much more detail, you would see me standing on as one of the persons in that photograph as well, and there is something written in Chinese, and which there is some sort of a forest and a mountain. This is what you would be seeing over there. Now if a computer is given down with the simple task of can it interpret this particular image, then how is it going to start? Now what it would be doing is something of this sort. It's going to break this whole image into some small regions. Okay. Now in the whole time, it's not seeing just one image, maybe it's seeing a million of those images, and over time it's learning what to do. So it's going to do something like it's going to break it down into multiple number of such small blocks and then identify what each of these blocks mean over there, and then from there it's going to look into certain things which it knows over there as having seen something earlier, and then finally it's able to look into the whole stuff and identify people, and then some sort of create a sentence. Now if you look at this curve over here, the fun which you see is that as you are increasing your experience, which is the more the number of images you are looking through, your performance is going to increase, which is sort of say accuracy in identifying objects, so the number of objects you can identify. So over epochs or over the whole data set, this is increasing, and this is when we say it is learning. Now all of these names are basically not real, so they are just indicator names in any way, so I don't know whether these were their real names or not, but this was just to make it as a much more compelling problem and give it a much more personal flavor. Now let's look at what it was doing when it was trying to learn, and that's about how was it learning. So you have this whole image. So the first thing which your computer program learns to do is divide it into number of segments, which are called as salient segments. So these are the segments which define a certain object present over there. Now on each of these salient segments, it would try to objectify whether it can identify certain objects present in those salient segments over there. Now from that objectification, it will try to detect what those objects are, and say it's able to detect humans over there by seeing that there are human like faces. And then on the other side of it, some of these segments which were not properly detected, although they were objectified, they were not detected, they might be going down onto another pipeline where the purpose of this pipeline is to recognize these inanimate objects. Now from there, it can recognize these humans if there is a large database over which it has looked at all the faces of those humans, and from there it can actually go on to describe this whole scene by using this complete information. Now this is a way in which a computer program is going to do, and inherently, if you look at this whole paradigm in which it is solving, you would be seeing that this is a hierarchical framework in which it is solving. There is necessarily a hierarchy. So you need to first find out the salient segments, and then you would be objectifying. Then some parts of these objectified things you would be detecting humans, on some of them you would be recognizing inanimates, and you come down eventually to a place where you are able to close the whole pipeline and able to describe the scene. Now the question is, we do agree on one part, that this is a hierarchical process in which any sort of a vision problem is being solved today, and any kind of a computer vision problem, any sort of a medical image analysis in respect of computer vision is also being solved today. We agree to this whole point over here. Now the question is this whole thing unique, or can there be a non-uniqueness to this hierarchy as well, which is what we need to answer. Let's do a very simple experiment over there. Let me just take a clone of the same network and try to reshuffle around certain of these blocks, and then again reconnect all of them. So once I have done all of this, what you would see is that in both of them, on the green pipeline as well as on the blue pipeline, you actually have the same number of blocks, the same blocks doing the same things. But what I have done is the order in which they are going to do these is where I have brought in a difference. Okay. Now this is also a valid one, this is also a valid one. Both blue and green are valid ways of solving the problem. The question comes is, which one do I choose? This is something which is going to plague the community for quite long, as to which pipeline. So there can be person A who says that I will go by pipeline green, there can be person B who says I can go by pipeline of blue, and you would keep on debating for say time immemorial as to who is correct, and there might not possibly be a solution. And that's how we see in recent days that somebody or else has a different way of finding it out, and nobody is very sure about whether their hierarchy is an absolute hierarchy in some way of doing it. Now in terms of an industrial problem, this poses a very major challenge, and that challenge is that since I am not able to define which is a very unique pipeline in the way of solving it out, so I will have to invest many more manpower in order to optimize which of them is going to be my best product outcome over there. So typically the cost factor associated with developing a software for medical image analysis in this case would keep on increasing by the number of such replicable models which we are going to create, such identically similar performing pipelines. So although the codes will be same which are being developed in each of them, but then there will not be much of a code reuse going down across them. There will be a team of people who will solve out on the green pipeline, there will be a team of people solving on the blue pipeline, and I don't know, there can be infinite such number of pipelines actually. None of us know. So this is going to escalate the cost if my final objective is to come up with the best software to solve this particular problem. Now this is one problem, this is one challenge. The question is this the only challenge which is going to keep me preserved? Now that will not happen, because if you look into it, say let's look into one of these blocks which is about detecting humans. Now one way of detecting human may be I take a patch of that salient object, on that I find out certain features, so maybe local binary patterns, wavelets, and histogram of oriented gradients. I use all of them, I plot them onto a body part recognition manifold which is going to recognize my body part. So there is a head, there are 2 arms and there are 2 legs. Now based on that it can project it onto some sort of a human appearance manifold, and from there it will recognize that this is a valid human. This is one way of detecting that there were humans present on the image. There can also be another way of detecting it out, and so certain different person might say that what I would do is I would do a chroma clustering and a posture realign, and that would lead to finding out some sort of a silhouette over there. So person in different poses, how they would look like, and then you can have a library of these silhouette images and you just match down with the silhouettes. Now once you have matched down with these silhouettes, then you can actually project it this matching distance onto certain sort of a manifold and then be able to recognize humans. Now you see that even for detecting humans there can be the first block, there can be the second block, and both of them may be equally good and equally bad, and people would still just be keeping on arguing as to which one to use. Now this is a major problem, and these are actually very big problems which are plaguing the community today, and that's where deep learning comes to play. Now I would draw your attention onto a problem which we solved a few just 2 years ago, and what this whole problem was that say you have some sort of a computational model which finds out so this is about computational imaging as we had discussed in the previous ones. So where you would be looking into different natures of tissues present by just looking into the say ultrasonic signal or optical speckle signals over there. Now over here we would be having one model to extract out features, which is again guided by certain good knowledge about the physics part of how signals get propagated. Then we will have another model just to map these features extracted onto these tissue types over there. Now the question comes is, can I have one single model which can do all of this, or in a very simple terms, there is a lot of mathematics which goes into this whole place, and for a lot of people how this would appear is as if within that mathematics there is some sort of a weird miracle which happens and this is solving my whole problem. So if I don't want to do this, and can I get down an actual network over there which will be solving the same problem without me having to bother as to what sort of mathematics is going on. And in fact it's not so hard to imagine, because we have a very simple solution to this one as well. So what we proposed down was something like this. It's called as an autoencoder solution. So this in the subsequent slide you will be having a view of what they mean down, but if you look over here, say I take down one small patch from this image and then I'm going to feed it through this small block which is called as a denoising autoencoder. Whatever comes out from the output, I again feed it into another block which is also a denoising autoencoder, but this block takes an input from this block only. This block cannot take an input from here. This is what you need to remember. And then you keep on passing this through over here, and this thing is called as logistics regression layer, which is very similar to a sigmoid transfer function actually, and you are able to find out a probability of the different classes of tissues. So over here I basically have 4 different classes of tissues which are marked down on this image, which is an OCT image of the skin. So this is my whole pipeline which I would be solving, and how this whole pipeline, and inherently assuming that this pipeline somehow learns by itself to solve all of this complex mathematics which we were thinking of as a miracle which is happening in the earlier case. Now if we look over here, what we design is a network very similar to a neural network, but it's with more number of hidden layers over there, and that's the point from where comes the term called as a deep neural network. So you increase the number of such hierarchical representation layers under the assumption that on each of these hierarchical mappings you would be mapping down one small extra feature, extra amount of information onto your network, and that will help you in solving a much complex problem onto a much simpler solution over there. So if you look into this particular network over here, it appears very similar to a multi-layer perceptron. So you basically have one layer of single perceptrons over there, you stack on these layers and you keep on continuing, and that's how you are going to get this whole network. The challenge obviously exists in how you are going to train this network, and that's where a lot of people will come into with their expertise, and we will also be solving a subsequent problem where I would show you how we can figure out a way of taking care of these problems as well. But the challenge is that once I have somehow been able to train this network, do individual representations over here make any sense, which is, say I have this first neuron, second neuron, third neuron. These are, say there is a patch of 5 cross 5, so there will be 25 pixels over there, and I'm just ordering each of these 25 pixels over there. Now all of these 25 pixels connected to, say, this first node over here. So there will be a 5 cross 5 weight matrix which is also going to connect to this first node. For the second node also I will be getting a 5 cross 5 weight matrix which is going to connect. For the third node also I am going to get it. Now the point is, are all of these weight matrix going to be the same, or are they going to be different? Now if they are different, how will the network make sure that they are different? These are questions which we need to answer. On top of that, so this is from where I am going to map down to my first neuron. Similarly, I am going to map down to all the hidden neurons over here. Now from these neurons, I will again be having my weight matrices connected down to each of these neurons over here. So these are going to be some sort of a dependent analysis of all the representations we are learning over here. Now that's where comes in the beauty of a deep neural network actually using a set of very small operations in order to solve a very complex function. So let's look into what that meant. So in terms of learning my representations, what I would do is, say I have this neural network which I have learned on over here. Now from that, let's look into the first representation over there. So what I have is basically a matrix of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it's a 20 cross 20 matrix, which means that I basically have 400 nodes over here. Each of this patch is again made up of a set number of points. So over here this is basically 21 cross 21, which is the total number of nodes I have over here. Okay. Now each of them, if you would zoom into them, you would be looking that they somehow look like wavelets. They have some sort of a definition, and some of them are inverse form of it. So this one looks like more of a Mexican hat kind of a wavelet. This looks like an inverse of that particular wavelet, and there are some ones which are perfectly like flat regions like this one, or you can have a perfect white one which is a DC shift or a unity multiplier over there as well. So there are multiple of them, and a lot of them actually look very similar to each other. So they might be different, they might be similar as well, but what comes out at the end of here is that here whatever it learns, each of them is basically some sort of a correlation kernel which it is learning. So your feature extractors are getting learnt over here itself without me telling what kind of feature extractions to take place. So your network is just doing classification by taking in an image, but one image, it's going to extract out different features. So these feature extractions are what's happening over here. Now let's look into the second layer over here, what happens over there. Now on this, this average gray value is basically a commodity of 0 that has an intensity of 0. Wherever it's a white small dot over there, they are all bright spots which are corresponding to a very high positive value, and the black dots over here, they correspond to a very low, very high negative value over there. Now what this does is, this particular matrix will be mapping all of this. So there are 20 cross 20 or 400 such nodes which are mapped over here, and here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there is a 10 cross 10 or 100 such nodes over here. So each of them is a 20 cross 20 or 400 patch element. Now each of them is giving a weight to each of such correlation kernels which we had learned, or some sort of features which we were going. So this is a weighted combination of features which is getting learnt in this second layer. So similarly, if I keep on looking at the third layer, fourth layer, fifth layer, they would just be looking into a hierarchical combination of how we can learn down these features one by one. And this is where I meant to say that a deep neural network itself can synthesize the hierarchy from the data without you having to explicitly say how to synthesize this hierarchy, and at the same time it would also be doing a classification problem for you. So the hierarchy gets synthesized, as well as how you are going to combine each of these features at different levels of hierarchy. All of them are getting synthesized together. Now if we get back to our old problem on that scene classification where there were 4 people and everybody, and then we had this parallelism that there can be 2 different possible hierarchical combinations in which we can solve the problem. And the question which was in our mind is that if we have such two different combinations, then which one do I choose? I just cannot arbitrarily choose one of them. There should be some basis of choosing it down. Now, if I say that today we have techniques where you can just give a simple network over there and let the network decide the order in which it can choose a hierarchy, won't that be making much more of an exciting proposition for us? Because we will not have to bother anymore with feature engineering, we will not have to bother anymore with classification margins and stuff. We can just feed in images on the input side of it and just get a classification over there. Under the fact that we can somehow code this whole neural network, this can be computationally solvable and tractable, the gradient should be existing, there should be a error back propagation throughout it, and we are able to solve it. We would definitely be making lot more promising results onto it, and this is one particular result which I would like to show. So this is about optical coherence tomography OCT image which we had studied about. So this is an OCT image of a skin of a mice, and this is about the skin of a mice which is healing. So there was certain wound in which the skin was peeled off and the mice is now healing, and over here you would see that the epithelium is not yet clearly formed, and over here some part of the epithelium is formed, and the full thickness of the skin is not yet restored, because typically it's about this order of a thickness, which is roughly about 1 millimeter thick, roughly about 1 to 1.5 millimeters thick, but this is roughly 0.5 millimeter thick, so it's still in a healing state. Now on this one, this was the ground truth by looking into the histology which was marked down by a histologist, and this is the sort of predictions which we are able to get down over there, although they look very shabby, but given a point that the whole network was actually trained with very healthy samples, where it was a full thickness skin of 1.5 to 2 millimeters on which these labels were obtained, and each single layer was perfectly present, so your speckle formation was also in a much more clearer way. So here we have been able to reproduce a similar way over here, so you can get a very clear and distinct epithelium, you get the papillary dermis coming down perfectly, the dermis and the adipose appear very perfect over here, and here we never used a single sort of feature extraction over there. What was fed to the network was just these small patches, and what it was asked to predict was just these tissue levels over here, and the network learns by itself what sort of features to extract and what hierarchy should it be following in order to get to this particular problem solution. So this is the beauty of deep neural networks, and with that I would conclude the first part about deep neural networks. In the subsequent lecture we would be studying about the history of deep neural networks and how they have been working the way they are working, and a survey of certain examples where in the recent past we have had great successes in solving medical image analysis problems with deep neural networks, and so following that I would also be entering into showing you the solution to using a deep neural networks in order to solve the same ALL classification problem which we were doing by the classical way of first extracting features and then doing a classification. So here we will start with the point that can we just put in the image itself as it is and solve the whole problem where it gives me a classification coming down to it. So let's be excited for the next part of the lecture. Until then, thank you.